I please welcome Mr. Mike Rosenberg, CEO Prieto Battery, who shall be sharing his deep insights on high energy density 3D batteries that fully charge in 3 minutes. May I please request Mr. Mike to please come up on the dais.
Good morning, everyone. It's a pleasure to be here. I'm Mike Rosenberg. I'm the CEO of Prieto Battery. And what I'm going to do today is talk to you about a revolutionary new battery. It's a 3D architecture. It's a battery that Dr. Amy Prieto developed. She's our founder. She's very well known in the battery industry. She's got a number of different industrial awards. She got the U.S. Presidential Chemistry Award for our technology. Our battery's in the National Museum and the Smithsonian. What she decided to develop was the holy grail of all batteries. It's a 3D battery that combines the best of high power density with high energy density. So you get a fast charging battery, hyper fast charging battery with high energy density in the exact same battery. So it's revolutionary, new, and we're very excited about it. Now, today's lithium-ion batteries, they're not good enough. We've been in India now for a week, and we can see that a battery that takes an hour to charge is going to be really hard to implement here in India. I mean, we've seen gas station lines of 70 cars long or more trying to get a fueling redone with 3 to 5 minutes. How do you do that with a charging station that takes you an hour? It's just not going to work. You need to have a faster charging battery. India has very high temperatures, 55 degrees C. That's going to require battery temperatures that are going up to 80 degrees C. How does that work with a traditional lithium-ion battery? It doesn't. You need to have something that has a wider temperature range. Thermal runaway fires are still a problem. I mean, we just saw a presentation talking about how do you keep fire mitigation from happening. That needs to be resolved. These batteries have lack of range, they're heavy, and they're too expensive. So again, to get into the Indian market here, you're going to have a battery that's going to be better, that can address these issues. We have that battery. Today's batteries. So if you look at today's batteries, they're 2D batteries. And what we mean by that, it's a kind of a layer pancake. So what you have is a current collector, you have an anode, a separator, a cathode, and another current collector. And if you want a high energy density battery, you have to put more energy into the anode and cathode, so you make those layers much thicker. And if you make those layers thicker, that means the lithium ion has to go from one side to the other side. It's a much more arduous path to get there, and it becomes very slow. So you have a very high energy density battery, but very slow charging, very low power output. If you want a fast charging battery, you're going to make those layers very, very thin. So the lithium ion can go back and forth very quickly, but now you have no energy density. So this has been a conundrum for battery designers for decades. How do you have a battery that has both high energy density and high power density or fast charging in the same battery? People are still trying to figure this out and trying to get that optimum balance. A 3D battery does both. And how do we do that? What we've done is we've created this 3D battery. And we start with a high porous structure that has a high surface area. And then we coat those individual strands of that porous substrate with a very, very thin layer anode, a very thin separator, and a very thin cathode. So when you look at it, you have a very short pathway for the lithium ion to go back and forth. So it's a super fast charge. Yet you have a lot of surface area within that structure. And this is sometimes a better way to look at it, is how we actually put this together. So we start with the copper foam on the upper left-hand side, and we electroplate our anode on top of that, which creates a very thin microlayer anode. And then we do the same thing electrically with our polymer separator, which is our electrolyte and separator. Again, very, very thin. And then we coat that with our cathode. And then we attach a current collector to it. So what you end up having is a lot of surface area around each individual strand. So you get a lot of energy density, so a lot of materials in there. But the layers are so thin, you get super fast charging. So what does all this mean? It means that we have a battery that's hyper fast charging. It charges fully in 3 minutes. And you can imagine in the Indian infrastructure here. If you could pull into your service station on your way to work, get a full charge in 3 minutes, or get a partial charge, half charge in a minute, that makes it doable. It's very fast, very quick. Extreme temperature operation. Our battery operates from -30 all the way up to 100 degrees C. It not only operates, but it charges in both those extremes. Again, when you start looking at the Indian environment, to have a battery that can work up to 80 degrees C without any issues, changes the way you design that battery, changes the way you design that pack, changes everything. Safe. Our battery is safe. It won't combust. There's no thermal runaway. We've done a number of abuse tests on it, short circuit, overpotential, thermal abuse. It's completely safe. Again, changes the design of the entire pack. This is a higher energy density battery, so you're going to have basically one half the weight and 1/3 the size. So that gives you flexibility again on your designing. You can have a smaller battery pack with the same range, or you can create the same size battery pack and get larger range. Again, creates a completely different value proposition. Our manufacturing is low cost. Again, it's very green, so we expect this to be one of the lowest cost batteries there is. And then the jaw-dropping power is the opposite of the fast charging, which means that you have very high power outbursts of power, up to 20 C. So that enables all sorts of different applications that you can't do with traditional lithium-ion batteries. This is a picture to show you the difference between a 3D battery and a 2D battery. These two batteries are the exact same capacity, made from the exact same material. The only difference between these two batteries is the architecture. So as you can see, the top one is the 3D battery. It's way smaller footprint, and that's because of the 3D architecture. So that's the benefit that you get from a 3D architecture. And again, when we look at this, this is, we believe, probably the world's fastest charging battery. 3 minutes. We haven't seen anything that's even close at this stage. Advanced solid-state batteries, they're talking about a 10, 15-minute charge. If you look at that, in 3 minutes, you're only going to get 20% of your battery capacity. On a lithium lithium-ion battery, it's usually about a 2-hour charge, something of that nature. That's only 3%. So this is fundamentally different. It's game-changing. It's world-class. From an operating perspective, traditional lithium-ion batteries have a very narrow operating window. It's typically between 15 and 35 degrees C. And if you get outside of those, if you get too below that, you create damage to your cell, which then results into potential thermal runaway, fire, and explosion. If you run above that, you risk thermal runaway, fire, and explosion. Again, our battery operates comfortably between -30 and 100 degrees C. And then it's safe. Like I said, we've done all the testing, thermal abuse testing, we've done overpotential, we've done the nail penetration test. So as you can see, the nail went through this battery. There's no off-gassing, there's no swelling, there's no temperature increase, there's no thermal runaway, there's no fire and explosion. You can look on the internet and you can find numerous examples of this on a traditional lithium-ion battery, and it's violent. It's explosive, it's very violent. This is a safe battery. From a manufacturing standpoint, when Dr. Prieto started the company, she's like, I'm going to go after this holy grail of battery. And the 3D concept had been out there, it had been in university papers, white papers and such, but nobody had ever really made one. And she decided, if I'm going to make it, I need to be able to manufacture this at low cost, high volume, and high quality. Otherwise, what's the point? So she literally started with her team with a whiteboard and said, okay, what are all the processes to manufacture a battery? She put them all up there, and then she started crossing off the ones that are too expensive. She put up all the materials, crossed off all the ones that are too exotic, too costly. So she took off things like clean rooms, dry rooms, high temperature sintering, ceramics, exotic solvents, binders. And she came up with electroplating as the process to make this work. And electroplating is done out of water at room temperature and atmospheric pressure. It doesn't have any binders, no exotic solvents, nothing of that nature. It's also been done and used in semiconductors, solar manufacturing, airplane manufacturing, aerospace. So it's a well-known technology,
And it's done at very high quality, very high volume, and low cost. So it hit all those objectives. But what that meant is that then she had to invent all the different aspects of the battery to fit in with that manufacturing. She's done that, so we have a process that now we manufacture at the lab scale on our bench that's water-based, room temperature, atmospheric pressure, no expensive exotic materials, nobody's wearing hazmat suits to be operating, there's no dry room or clean room. So it's going to be a low-cost, green manufacturing process. And when we look at it, this is an example of a process that's being utilized today. It's a solar manufacturing facility. This is manufacturing SIGs, electroplating SIGs. The web width of this metal material that they're electroplating on is about 6 feet. It's continuous, it's high volume, high quality, low cost. And you can see the operator, he's wearing a t-shirt, he doesn't have any fancy hazmat suits on or masks or anything of that nature. There's no clean room. You look at the room, it's a standard warehouse. You can see the drywall. There's nothing exotic about this. If you look at a solid-state battery manufacturer or a lithium-ion battery manufacturer, they have a special building. They have dry rooms. They have clean rooms. They're using high-temperature processing. They use exotic chemicals, processes. That's not low cost. This is a low-cost process. And we've had equipment manufacturers in our facility looking at our processing. They understand it. They know how we can take what we do on our lab bench and take it to this scale. So we're very excited about this. We've done some preliminary cost estimates from a capital perspective, and we're probably 20%, 10 to 20% of that of a solid battery manufacturing facility, pilot facility. A standard solid state pilot facility, 10 megawatt hours or thereabouts, would be typically $150 to $200 million. We're more in the $20 to $30 million range. So this is going to be a low-cost process. We've done rapid scale-up. This is a scale-up that we've done from our first 3D interdigitated battery starting in August 22 up to a 1 amp hour battery earlier this year. It took us about 6 months to do this. This is a rapid scale-up. Other people have done similar scale-ups in different technologies that have taken 6 to 8 years. So this shows the robustness of our technology and the power of our technology to move very quickly. And because we've already done the manufacturing design and process, we believe that this shows that we'll be able to scale the manufacturing equally as quickly. So with that, that leads into this, the intellectual property. Sorry, one more slide before the final. We do have 28 issued patents on this technology, covering 7 distinct patent families. And we've applied for patents across the world where we'll be manufacturing and selling these products. And now finally, so we believe we can get to market very quickly with this technology. We're at lab scale today, but we came out of stealth mode, proving our battery and showing our battery's capabilities earlier this year, May. And we did that because we're looking for strategic partnerships. We have one strategic partner today in Stanley Black & Decker for power tools, but we're looking for additional strategic partners in different markets today. In addition, we're now looking to start the development of our pilot plant, either through contract manufacturing or building and designing our own pilot facility. We're going to do that in 2024. We'll use that to start our commercial operations. We'll use that for prototyping, validating the manufacturing, but also our initial commercial sales for smaller batteries. Same time we're doing that, then we'll start our design for our large-scale manufacturing facility. That would be in the 25, 26 standpoint. And by 28, 29, we will have a giga-sized factory battery production facility. We do expect to be in multiple markets, but in the partnerships we're looking for things that are synergistic with our power tool strategic partners' batteries commitments. But we see our battery being able to go into everything from EV tolls to EVs to medical products to consumer products, everywhere where you need a very fast charging battery, high energy density, and something that's safe. So we're very excited about it. And with that, thank you very much. I appreciate the time.
Thank you so much, Mr. Rosenberg, to share your deep insights with the audience and us today. May I please take this honor to share a small A token of appreciation on behalf of Informa Markets with you.